So the second day of 1.3 limits, we're going to finish up what you needed. For all the trig functions, it's just direct substitution. So you have the limit as x approaches c of sine of x, you plug in c, and you find the sine of c. That's legitimately all you do. So I have the limit of as x approaches 0 of tangent of x. So I plug in tangent of 0. And what is the tangent at 0?
No.
0.
Undefined.
No, it's 0.
Close.
Pi over 2, it's undefined.
Huh?
Pi over 2, it's undefined. But not at 0. Okay, so now I have the limit as x approaches pi of x cosine of x. So my rule says just plug in, right?
Wouldn't that just be cosine?
So pi of cosine of pi. Well, what's the cosine at pi?
At pi? 1.
Negative 1.
Oh.
So it would be negative 1 times pi, so it's negative pi. Okay, now sine squared, so the limit as x approaches 0 of sine squared of x. Remember that you find the value and then you square it, right?
Mm-hmm.
So sine squared at 0, well, sine at 0 is 0, so the answer is 0. So on your assignment last night, you kind of, like Riley said, she did it. You probably just went in autopilot and did it because that's all you do is just direct substitution. Okay, theorem 1.1 through 1.6 all use direct substitution. That's what we've already done. But what if you cannot use direct substitution, Cadence? Well, if you cannot use direct substitution, theorem 1.7 says functions that agree at all but one point, you reduce. Okay, so all these words say here, it says let C and A, don't write this down if it doesn't make sense to you. We're going to write our own words, right? So let C be a real number and let f of x equal g of x for all x not equal to C on an open interval containing C. If the limit of g of x as x approaches C exists, then the limit exists. So basically it says reduce. Then use direct substitution.
Because when I was trying to do these, I would put the 1 in and it would be 1 minus 1 over 1 minus 1. It would be 0 over 0, and then I tried to put in 0, and then want to take it, and I put D and E, didn't want to take that either, so I was just like, I don't know.
Okay, so reduce, then use direct substitution. Anytime you can reduce, should you always reduce before you do any math? Yes, it just makes it easier, right? So you first always try direct substitution. Direct substitution is going to fall apart here because what is your denominator?
0.
0, and I can't do that. Now, it maybe does not exist, but we don't know, okay? So we need to factor, then reduce. So we have a difference of cubes up there. So it'd be x minus 1 times square the first, opposite sign, multiply them together, and square the last. Yes? That pattern? So what can I reduce this to?
Yeah.
So I'm now looking at the limit as x approaches 1 of x squared plus x plus 1. Do you see that? Because at 1 is this open circle. We should know that. It's not in the domain, right?
Mm-hmm.
So that would be 1 plus 1 plus 1, which would be
3. That makes a lot more sense.
yeah. Good?
Yes.
Jaden, you good?
Yeah.
Okay. Okay, so strategies for finding limits. Learn to recognize which limits can be evaluated by direct substitution. Your first option is always direct substitution. It should always be your first option unless it tells you to do it another way, okay? It's the easiest, it's the quickest. Then, if you cannot do that, you need to, if the limit of x approaches c cannot be evaluated by direct substitution, try to find a function that agrees with f at all places. In other words, reduce, right? And that's not how you spell reduce. Reduce. If that doesn't work, if you still get 0 over 0, or you still get, it doesn't work, then we go to a graph or a table. Okay, so should we always do what first?
Direct substitution.
And then we should do reduce with then direct substitution, right? Or if those don't work, then we need to use a graph or a table. Make sense?
Yes.
Okay, find the limit using dividing out and rationalizing techniques. Okay, so dividing out is the same as reducing, yes?
Yeah.
And honestly, guys, I will even, if I know, that numerator factors, I would probably factor it even before I use direct substitution. Because I just trained my brain to look for that. Okay, so if I plug in -3 and show yourself, -3 plus 3 equals 0. So can I use direct substitution? No. So factors of 6 that have a difference of 1 are x plus 3 and x minus 2 over x plus 3. So now I can reduce out the x plus 3, and now will it work?
I got -5.
Yes. So -3 minus 2 is -5.
Cool, I can do it now.
Okay, now second one. Jaden gave me an evil look. Can I factor B?
No.
Nope. Well, it says use rationalizing techniques, yes?
Yep.
That probably involves a radical. And in this case, a conjugate. So I need to do something to the denominator, so I'm just not x, so I can plug in 0, correct? I can't factor an x out of the numerator, so I could multiply by this conjugate, which would be the square root of x plus 1 plus 1. Could I do that on the bottom and the top? Yes. So top and bottom. So difference of squares, so I'm going to square the first, so I just get x plus 1. And -1 times +1 is -1. Now the bottom is just going to be x times the quantity. Don't multiply it out. There's no reason to. You're going to use direct substitution, right?
Yeah.
Not a reason to multiply this out. Okay, so now let's substitute in what?
0.
0. So I get 0 plus 1 minus 1 over... Oh, wait a second. I messed that up. Sorry.
No.
I didn't... This is 0, yes? What can I do with this x and this x now? Reduce it to 1. So I get 1 over, right? Sorry. Now I have the square root of 0 plus 1 plus 1.
So the square root of 1 plus 1.
Say that again?
Square root of 1 plus 1.
And the square root of 1 is?
1.
So I have 1
1 half.
half. Now this one we had to use a conjugate because of that square root running around, right? Looks like fun, doesn't it? Okay, the last we could have graphed. So if we graphed it, we could see, but we've already realized that on a graph, on our calculators, it doesn't show me that whole, does it? No, but you could plug in 0 and see that it's undefined, and you just have to find where it goes. So a table works the best. And you would just build a table, and do you see that it's coming towards 1/2?
Yes.
Okay, special trig theorems. There it goes. I was switching and it wasn't switching there. Okay, 2 special trigonometric limits. The limit as x approaches 0 of sine of x over x is 1 every single time. So you need to have this somewhere and you need to highlight it and memorize it. And the limit as x approaches 0 of 1 minus cosine of x over x is 0. All the time, every time, no matter what.
I should be using my pens.
Okay, find the limit using the dividing out, rationalizing, or that rule that we've got.
1.
Hmm?
First one's 1.
Why?
Because there's a rule that says so.
No, the rule says sine of x over x.
What the heck?
Correct?
I guess so.
So, what can we do?
Put it as 1 and hope it's right.
Well, can we rewrite it? Tangent? What's tangent? So I have 1 over x, right? Isn't tangent sine over cosine? Yes?
Sure. Well, we ain't doing this again.
So could I rewrite this as sine of x over x times 1 over cosine of x? Can I do that?
How'd you get the 1 over x?
Well, because it's right here. I just pulled it out. Can I do that?
Yep.
Yeah, I can, because it's multiplication. So what do we know sine of x is?
1.
Or sine of x over x. We know that's 1, right?
So then it's
Well, if
just
we
1.
plug in 0, so I have 1 over the cosine of 0.
So it's 1 over 0 undefined.
No. What's the cosine at 0?
0. 1.
1. The x value. So I get 1 over 1. So I have 1 times 1, which is
1.
1.
Where do you randomly get 1 times 1 after?
Because this is 1. The limit of this is 1. Remember yesterday we just multiply them together?
But if it just looks like rule 1, it's gonna be 1?
No.
I think
No.
it is because I told you it was 1 and then it was.
That's not why it was 1.
I think that's literally why.
Probably not.
What did you do next to it?
What do you mean?
I
The
don't know.
1 came from here and 1 came from here. So 1 times 1. Because our rules yesterday said if you have one limit times another limit, you can just multiply the answers.
And then talk to me.
Okay, what about the next one? What happens?
Well, it's the second one.
No.
No.
The second rule.
Is there a 1 minus cosine right there?
What happens when I plug in 0?
0.
I get 0. It's not going to work, is it?
No, so it's
0.
rule 2. Because that one equals 0.
Okay.
But it's not
It
1
is not
minus
working.
Look,
Okay,
sine of
so-
0 is 0 over 0.
We're going to do some manipulation because we can. Okay?
I like manipulation.
You guys are, high schoolers are so manipulative. You should love it. Okay, so
No.
it looks like this rule, yes?
No.
Except for what?
Looks like the other one. No.
It looks like,
Like-
the rule 1.
If
Besides, there's a 4.
but there's a 4. So I can't take a 4 out, but could I put a 4 in?
You don't need to.
So could I multiply 4 over 4 times this problem? What's 4 over 4?
1.
1. So does it change it?
No.
No. So can I do it? Yes. So we're going to rewrite it as 4 times the limit as x approaches 0 of the sine of 4x over 4x. So 1 4 stayed in, 1 4 went out in it because it's at 4 over 4. Okay? Because 4 over 4 equals 1. So now, is this the same as this?
Yeah.
Yes. Now, in our brain, we can think of it as sine of y over y. Is that the same as x over x?
Yes.
Or just know if they're the same, the rule applies. So, we have a 4 times 1. So the answer is
4. The answer should be 1.
answer is 4.
The answer is 1.
So sometimes we're going to have to manipulate problems using like simple rules like multiplying by 1.
So basically, if there's a sign of anything x over x, the answer is the little coefficient there. Just made my own rule.
Probably not.
Hire me. I'm really bored of you.
Okay.
Thank God, Ms. Mick.